I just did this. Okay. All right, any other questions about the exam on Friday? Everything should be on the website, as far as I know?
According to her, yes, they're all posted.
Okay, they're all posted, and the keys are all posted too. So you guys should be able to have a look at those. So office hours, 3 to 5 tomorrow. I found out that if no one chimes in after 40 minutes, it shuts me out. I have to go back in. If you need time later on tomorrow night, let me know. We can set something up after 5. I just don't know when, unless you tell me. Some of you are working, I know. So that's fine. Last night I had a Zoom call at 10 o'clock at night. So this stuff happens. Anything else? Yeah.
Can you post a recording of the office hours?
Poster. Oh yeah, if that's okay. Yeah, I can record the Zoom. Yeah, sure. Hopefully that doesn't make people bashful, but yeah. Anything else? Okay. All right, so there's a lot of different ways of talking about the mechanical properties of polymers.
Actually, I forgot to ask something. For the exam, is it pen or pencil? Are you doing better?
Either is fine. Please don't challenge my ability to read handwriting. It's pretty good, but sometimes, it doesn't work. Let's see. Yeah. So many ways of examining the mechanical properties of polymers. So you see people try to treat it as if it's an inorganic, which doesn't always work so well. But there are a variety of different approaches to it that can be handled. One of the old ones is spring and dashpot models, which I used to teach for a few years, and then it's like, this is really a crappy model, so I stopped teaching that. So I've kind of gone to something that is a little more free energy basis than that, which I think captures a lot of aspects of polymers that are a lot more realistic than springs and dashpots, which are like a 1960s view of mechanical properties that people went crazy with for a while, but it just doesn't make sense and requires too many assumptions. And so what I talk about in this context is a free energy basis, which allows me to, discuss the issue of entropy and alignment, and kind of sets you up for talking about crazing, which comes after this lecture. And so it's a better approach, a more holistic approach to talking about polymer mechanical properties. And so we know aspects about polymer behavior and what controls it. And today you'll see more about entropy and the importance of it in terms of mechanical properties, where it also influences this process. And I will introduce the concept of crazing, at least the word. You'll learn a little bit about it, but then we'll learn a lot more about it next week. And how this is associated with oriented fibrillar structures that show up in X-ray patterns for polycrystalline materials. So just like we talked about last time, this can also be seen for polycrystalline materials via X-ray. No, I haven't been coughing all day. Dust inside the mask or something. We will also cover polymeric behavior versus temperature and the associated time-dependent internal processes. And so there's an aspect of temperature here that makes polymers different from inorganics. And so they don't behave the same way as you increase temperature. There's an aspect of entropic behavior that has to be taken into account. Let's see. So I think that's all I want to say here. And so we've already discussed the contribution of entropy to crystallization processes. And so we talked about the fact that in general entropy wins, but in the context of crystallization, entropy loses. All right, but we have this balance between enthalpy and entropy, which we're going to cover again here. It should make some sense knowing what we've talked about before in terms of the number of configurations and how that influences the energy of the system, that same aspect should be important when it comes to mechanical deformation, because again, polymers want to be random. And when we start straining a polymer chain in any way, we start taking away some of that randomness. We start decreasing the number of configurations it can have. And so this is all part of the clock diagram, which I'll refer to hopefully a couple of times here, and how the clock diagram talks about aspects of the amorphous components of a polymer microstructure being strained, whereas the crystalline ones are not. All right, so that comes to the forefront here again as well. So entropy contributes to the deformation and the response to deformation of polymeric materials. And again, from before, we talked about the fact that the strong covalent bonds within polymers deform very little. And so we just talked about that from the standpoint of what we see when the A and B axes in the unit cell strain a lot during an increase in temperature, whereas the C doesn't do anything, because the C represents the strong axis of the polymer chains. And so this is all part of this clock diagram and all part of what controls some of the aspects of what we're talking about today. So under applied loads, even when the chains themselves are either extended or contracted. And so there's an aspect of trying to protect these carbon-carbon bonds, basically, because you can't change their length, you can't change their angle, and so everything else changes, but those two things don't. So at elevated temperatures, thermally driven motions will tend to randomize the positions of these chains, and so if you give them the energy, they will try to minimize their energy by maximizing their number of available positions. All right, but that has to be done at a high enough temperature, which it turns out is available typically at room temperature. So everything we're talking about, which I guess if I was talking about metals or ceramics, I would say hundreds of degrees, but 25 degrees centigrade is enough with most plastics to achieve these types of changes in structure. So if we use a load frame across the street, then we're seeing these things in real time.
Correct me if I'm wrong, but entropy doesn't really contribute to crystallization so much as it's overcome by enthalpy, right?
Yeah, I talked about the fact that it's a balance between enthalpy and entropy, and in that case, enthalpy wins. But in many cases that we're talking about today, entropy wins. Okay. Anything else? Yes? Higher the entropy, yeah. So I'll just talk about this. The next content I'll talk about, which is entropic stiffness. All right. So these elevated temperatures attempt to contract elongated polymer chains. So if I strain a polymer structure, then that means there's a resistance to extension that increases with increasing temperature, and this is sort of the opposite of what you're used to talking about with inorganics, where this enthalpic elasticity takes place. And so if I take a metal to ceramic, and typically I have to go up to higher temperatures to start really seeing this, that material becomes less stiff. All right, the atoms move around, the lattice is a little more flexible. All right, those bond lengths will change as we increase temperature. Silicon is really good at this. And so it becomes softer. But in the context of polymers, what you're doing is you're giving those chains energy. And they're saying, well, I've got more energy, I'm going to try to maximize the number of configurations, and I'm going to try to pull the chains back to where they were before that mechanical stress was applied. Okay? And so there's this concept of stiffness increasing with temperature. And so the entropy that the system wants to assume opposes the mechanical deformation. So we talk about this in terms of being entropic stiffness. And so if we go back to the delta G equals delta H minus T delta S, we can look at it in the context of the mechanical properties, where sigma is equal to the modulus times the partial differential of enthalpy as a function of strain, as we apply strain to the system. And then we say minus T, in this case we have a partial for entropy as well, delta S as a function of strain on that system as well. And so, the polymer, as you should have internalized by now, is going to try to keep this from happening. It's going to try to keep this entropy change from happening. It's okay with enthalpy, but entropy it tries to fight all the time. And so we have what we're used to thinking about for inorganics, rigid resistance to stressing and bending, and then we have this delta S term, or the partial of S with respect to strain, which is the resistance to conformational change. All right, and so this is, again, where polymers shine, essentially, because they don't want to change their number of conformations because you change the number of configurations at the same time. And we talked about the fact if you take the polymer chain, a polyethylene, and stretch it out, so it's perfectly stretched out, all right, it hates that, all right? And that's what mechanical strain is trying to do to those polymer chains, extend them so they have fewer configurations, and they're going to fight back against that. And so what happens is we have entropic resistance that occurs, and it can be represented as a stiffness. Okay. Again, metal, ceramics, they don't do this. Entropy is not a factor. But with polymers, it's a huge factor. Yes?
So you were saying that stiffness increases with temperature, right?
Yep.
But if you like heat up a plastic toy or something, it feels less stiff, like as it gets warmer or hotter, right?
Yeah, so as you heat something up to the point of melting, then things change. So you go beyond the melting point, that's a different story. This is before melting. So we're talking about plastics in non-liquid form. Let's call it that. Okay. Yeah, that's a good question. So yeah, eventually when it melts, it's a liquid and it changes very dramatically. Yes.
This would be like heating up a plastic bottle that's been like you've blown hot air into it to elongate everything, and you heat it up and it contracts again.
You heat it up and do what?
You heat it up and the bottle contracts.
That's a manifestation of it. So, like that grocery bag I handed around. So, what I used to do, I'd come in with a blowtorch. I still have that blowtorch in my office. I hit the bag, and the bag burns, and it keeps burning. But at the same time, that bag shrinks. And what's happening is it's going from being a thin film to a fatter one, because this extended polymer chain, which gives us better mechanical properties, tries to unextend and it shrinks. All right. So if I take that polyethylene bag, which is yay big, and I shrink it down to its final densified mass, it's about that big, because you've just taken all that polymer film and stretched it, and it tries to reverse it if you give it any energy. Same thing happens with a water bottle. It all shrinks. All right, given enough energy. All right, and so kind of what we're talking about here is the mechanical response, which is happening during the mechanical strain process. But that's reversing this issue of entropic alignment. Any other questions? All right, so the rigid carbon-carbon bonded segments of the polymer chain can readily change the angles between adjacent segments without significantly changing the position of the atoms within the segments. What does this mean? This is that 3-carbon model that you guys have seen already. You have C1, C2, and then out here we have C3, and we form that 109.5 degree angle, and then we can take the C3, which is not fixed, whereas C1 and C2 are fixed relative to each other, and we can rotate it around. So it forms a cone with respect to C2, but it maintains that 109.5 degree angle. All right, and so we talk about this from the standpoint of helping crystallization to occur, but I'm talking about it here from the standpoint of being able to readily change the angles between adjacent segments without significantly changing the position of the atoms within the segments. All right, that's what I'm talking about. It's got all this ability to move and try to go back to the higher number of configurations arrangement. Okay? Especially if it's got the thermal energy to make that happen. So that thermal energy will drive random orientations to maximize entropy, which minimizes energy. And this provides a virtual stress that resists tensile deformation that would otherwise align those segments within the axis of the principal stress. So entropy can resist or reverse, and we'll talk some about that further on. I'll start giving you some data, applied stresses and strains in these polymer systems. Okay, and this should make sense. I keep talking about entropy, and entropy is important in mechanical stress, just like a lot of other things in polymers. Any questions about that? All right. And so one of the confusing things about this is that polymers are like other materials. We have both reversible and irreversible components to deformation. And of course, the entropic one I just talked about, this stress, it's trying to reverse it. It's trying, oh, you stretched me out, I'm trying to go back to being unstretched because I have more configurations if I do that. And that's what we see with these plastic bags. We have irreversible or plastic flow that does take place. All right, so if the polymer chains are doing their thing, but if you really deform that material, and you'll see some examples of that when we talk about necking, it can only reverse so much of that. All right, and initially that's a pretty small component, but as the process of stretching or deformation or extension proceeds, then that component of plastic deformation, which is a really confusing term. It's the irreversible deformation. We borrow this from metals and ceramics because they can undergo what's called plastic deformation as well, usually under very high conditions of strain. But this is what we think about when we say there's a component to it that doesn't get reversed by the drive to maximize entropy. And so this strain softening behavior is usually followed by strain hardening. And you guys hopefully have heard this term. Remember, this is where in metals all the dislocations show up and bang into each other. We call that strain hardening. Here we kind of borrow that term, even though there's no dislocations at work, which can stabilize the sample. And so I'll give you some examples of this in a minute. And one other thing that's important here is that these are plastics, and they're here at room temperature, which normally for metal ceramics isn't a big deal, but for polymers there are lots of things in the environment that can change that. Environmental fluids, we already talked about temperature, and various gases can play a significant role in influencing these behaviors. And this is especially going to become obvious when we talk about crazing later on. We have plastics that under normal conditions, they don't craze under load, and then you bring some acetone into the room, and suddenly they start crazing because the acetone affects the plastic. All right, and so these are normal things with plastics, and so this is distinct, at least normally, from inorganic behavior, except for some glasses and things like that. It's not normally something that we consider to be significant when we talk about metals and ceramics. All right, and so something that hopefully looks a little familiar is this graph here, where we talk about deformation of a material. It's made of plastic, but in general, when we talk about plastics, we have what's called either shear yielding, which we'll talk about in a second, or crazing, which we'll talk about more or less in the next lecture. In the case of shear yielding, we have a force displacement curve shown here for polyethylene having a high crystallinity. All right, so this is kind of the clock diagram brought to life. At least, hopefully, that's the way you can interpret it. So we start out, and this is a little odd for us. We start out with a rectangle. Okay, we know why we don't like rectangles in load frame testing. Why do we not test with rectangles? What do we test with first off? Dog bones, yes.
So you need to have a concentrated point for the stress to accumulate. If it's just a rectangle, that's going to cause problems.
It can show up anywhere in the deformation of it, yeah. And the other part of that, the reason why it gets really skinny, is we want plane strain. We don't want things that come out of the direction of the applied stress by the load frame. So we like dog bones because it gives us those two things. But if we have polyethylene and things go well, it doesn't start happening at some weird spot because it's not a dog bone, what you'll see is this type of behavior. So we strain the material, and this should be recognizable to you as the elastic component, right? So if it goes up, if it's silicon carbide, it goes straight back down. All right, highly elastic materials do that. So we have this elastic component, and the same thing's true for the polyethylene. If we stop this process at some point, it would come straight back down and not change shape. But what happens is we initiate the process of shear yielding. At this point in the stress strain curve, and that shows up as the nucleation and growth of this neck. And so it's a rectangle, it's a rectangle, it's a rectangle, and bang, it's no longer a rectangle. It's got a neck now. All right? And then what happens is we go from, let me go to this. We go from here to there to there. And that's happening during this process of continuous growth. All right, so we're at a continuous value of stress, and we're getting dramatically increasing values of strain. So the neck starts, and then starts shooting across the length of the specimen, and starts making it really, really long. All right, and this is the easy part. Obviously, we're not changing the stress. It just keeps growing and growing and growing. Where is this happening in the clock diagram? Yeah.
When the chains are becoming more, they're being broken, and
They're what?
when the chains are being broken and spreading out.
That word broken. What do you mean broken?
The secondary bonds are being broken.
Secondary bond, okay.
They're being spread more spaghetti-like.
They're being spread, but of the two phases in the clock diagram, which phase is doing this? There's two phases, right?
The one where the crystals are being split apart.
No, it's before that happens, yeah. So it's the initial part of clock diagram where only the amorphous stuff is being strained. All right, that's the easy part. It should make sense that corresponds to this easy part. The amorphous doesn't have any structure, there's no crystallinity to it. It doesn't like this process because you're taking away configurations, and it'll try to go back, but it's pretty easy to do. All right, and so that's that part of the clock diagram that corresponds to the amorphous components. Then when we get out here, then we start to get this crystal disruption, if you want to call it that. And that's harder to do because now you're taking crystals and starting to break them up. All right. And then at some point, ultimately the whole thing fractures. Does that all make sense? I mean, certainly the first part, the amorphous component moving around, that's easy. And so that's why it's this constant strain, it's constant stress process, but increasing strain. All right, any questions about that? Hopefully it makes sense. You guys, the clock diagram is going to be on the test, so you guys should certainly be familiar with it. Oh, I should point out that this is lambda. Again, a lack of imagination. This is it goes from 0 to 1. It's now 200% longer than it was before. So this is a lot of strain in the system. All right, and so the neck extends up the entire length of the sample. Again, borrowing from metallurgy, we call this cold drawing. Constant tensile force elongates the sample by several times its original length. So lambda again, 1 is 100%, 2 is 200%. All right, the stretching continues. The force increases up to the point of fracture. Shear yielding can also occur without necking, and this is one of the really annoying things about plastics. Result in continuously growing homogeneous plastic deformation. This process of shear yielding is typical for all semi-crystalline polymers and is also going to be visible in amorphous polymers. So, take it as sort of the average for these plastics, and again, connect it to the clock diagram, and you're typically going to be okay. But there are always exceptions with plastics. And it can go back and forth between shear yielding and crazing, as I'll say in just a second. So it's very, very annoying. Later on, there's a video I'm going to make available to you that tries to connect all this in the context of strain rate, which is really interesting. Any questions so far? All right, and so if we're looking at something under a microscope, this is kind of what it looks like when those neck regions develop. This is stretched amorphous polycarbonate, and so we've taken out all the crystals and made it very simple. This visual phenomena called shear bands will be observed when that neck develops. And so you can actually see this as this shear banding process, and the shear bands extend out and continue the growth of that neck. This is preferentially oriented along the directions of maximum shear stress, if you guys remember that from statics, I think. You still take statics, right? It's a joyful process for everyone, but yeah, it's the same thing. And so that's happening in this context, and you can visually see it. It's not a very well understood process, but shear bands do occur very commonly in plastics in this context. We understand it in plastics even less than we do in metals, which is not very good. Okay, and then I've been talking about crazing, and I want to just show it to you briefly, but we'll go over it in a lot more detail later. Crazing is something that can also occur in materials, and this is a great example of a polystyrene dog bone in which we're seeing these white lines shooting across the specimen. And we'll talk at length about what those white lines mean. And this is another route of version of yielding that can be observed that isn't necessarily going to cause neck growth at all, but it's going to cause these small regions, these white lines, which themselves are areas in which the plastic is being stretched. And we'll talk about what that stretching means. And so strain is increasing whenever one of these lines occurs. And so we see this with polystyrene and the load frame very, very easily, very, very quickly, especially if certain solvents are present. And so that's something that in the lab we can see in real life. You might have to work a little bit harder to see this with some plastics. If you take like a plastic coat hanger or a thick piece of plastic and you bend it back and forth, I don't know if you've ever seen this, you see some whitening underneath the surface. All right, that's crazy. These very small lines that show up and refract light and make that white color appear in the context of these plastics. And we'll talk more about that next time, just make sure that you kind of have some idea of what this means. So unfortunately, shear yielding and crazing are not mutually exclusive. Both can happen at the same time. One can follow a period of the other. It often depends on stress conditions. So how quickly you stress something, for example, or the temperature environment that are present in these systems. Again, plastics they're not like metals and ceramics. They're affected by a lot of stuff in the environment. In either case, the amount of flow prior to fracture is what determines the net ductility of these systems. In tough materials, and you guys know what tough means, right? There's the two definitions, the legal one that tells you nothing at all, and the other one which has to do with the resistance to fracture after damage has been added to the system. All right, that's these tough materials. Unsurprisingly, much more energy is dissipated by yield processes prior to fracture. For example, polyethylene is typically pretty tough. In brittle samples, these can often break without much preceding flow at all. So for polystyrene by itself, pure polystyrene is a classic example of that. And that's what that dog bone was. This is not rubber toughened or hipped polystyrene. It's just pure polystyrene. It is going to behave like a brittle solid. You add rubber to it, then you'll see a very different set of behavior. You might see shear yielding in polystyrene with rubber in it. Would not be surprising at all. Okay. Again, they can go back and forth. All right, and then this depends very strongly, as I mentioned, on rate and temperature. And so this is a good example of PVC. And again, we're talking about not the PVC that you can buy at Home Depot, because that's full of plasticizer. This is pure PVC, although it also is significant for the pipe you buy at Home Depot, as we'll discuss in a second. Tensile deformation at different rates and temperatures. So let's just dive right into the data here. So we're looking for the stress strain behavior of a piece of PVC at strain rates of 0.0004 meters per second all the way up to 7 meters per second, which I looked it up, it's about 16 miles an hour. All right, so pretty fast. You guys don't do this in the lab. All right. And so what you see with these very slow strain rates, you're looking at significant amounts of strain before fracture, and you're also looking at a long period of deformation. And so this, at this particular rate, we would think of, because of the area under the curve, this is where it kind of helps, is substantially larger, we would think, oh, this is PVC, it's pretty tough stuff. It goes out to these relatively large areas. But if we instead run it at 7 meters a second, it acts like a classic elastic material. It goes up, has a little bit of extension, then it breaks right away. Why is this happening?
The chains snap if you try to form them too fast.
What does too fast mean?
Basically, before they... I don't know, it means...
You're on the right track.
Literally too fast. Like, if you pull something apart slowly, the chains have time to adjust and
exactly.
like, reorient themselves. If you go just like this, they don't have time to move, so they snap.
Right. So it's all about chain motion, and chain motion takes time, all right? If you don't give it any time, then we don't get chain motion, and it acts like an elastic material, all right? So very slowly, chains can move around, you get lots of strain out of it, but if you don't give it any time, it just snaps, okay? And then in the context of temperature, we have a very similar behavior, and this is the one where the stuff at Home Depot becomes important. If we're at 70 degrees, that PVC, and you never see this in the environment, about 45 degrees, that's like the Australian desert, there's 45 degrees centigrade. 70 degrees, you'd say PVC is relatively tough. 40 degrees, it still looks pretty good. Room temperature where we live mostly is, except in this classroom, it tends to be relatively stiff, okay? And minus 30, it's also relatively stiff, okay? So what's going on there? First off, why is there such a huge difference?
More heat, more energy.
More heat, more energy, more vibration. Remember, heat equals vibration in polymer chains. All right, so don't think of them as hot, think of them as moving slowly, moving rapidly. Here they're moving rapidly, and whatever strain rate is being used here, it can strain to relatively large amounts with that much thermal energy available. You start taking away that thermal energy, and it can't strain very much, even at the same strain rate. Does that make sense? Now, where this is important, we had this thing with Columbia Gas a few years ago where they had problems with when you bring in natural gas into a house, it comes up out of the ground, and in many cases it comes up out of the ground in a PVC pipe and goes into the house. And so typically out in the plains of northeastern Ohio, when the winds sweep in from frigid Iowa or wherever they're coming from, the PVC pipe would start to get pretty brittle because it would be in the minuses, all right? And so they had issues where if someone came along and said, oh, let me hit this with a wrench, that plastic pipe would shatter and all this natural gas comes out and the house catches on fire. All right, so this can be significant, even for things that are as heavily plasticized as PVC pipe is. So there's definitely a temperature effect that can be important here. So yielding is based on specific relaxation processes that are both rate and time dependent. Rate and temperature dependent, I mean. So you have to think about both. We talk about polymer chains when they deform, chain motion is very significant. It takes time, all right? It doesn't just pop through things like dislocations. They typically pop through the whole matrix instantaneously. Polymers, it doesn't work that way. Too fast deformation can not give these mechanisms enough time. Too low temperatures can give you a glassy-like behavior and make something look relatively brittle. Any questions about that? Yes?
Yeah, you said before the higher temperature would make it stiffer, but no, it doesn't seem to be so.
Higher temperatures can make it more resistant. It doesn't necessarily make it not deform at all. Okay, so it really has to do with the amount of energy that has to be applied. Right? But once you've exceeded that energy, then it can start to respond to the higher temperatures and start to deform more easily. Okay, so entropy still works against it, but you also have all this energy available that allows it to overcome that. Any other questions? All right, and so strain in polymers is always composed, as I said earlier, of both recoverable and non-recoverable components. So recoverable means If entropy has its way with the system, it pulls it all back to where it was. And then the non-recoverable is a plastic strain, where the material gets moved around to the point where it can't go back to its original shape. And so we have these two components of strain, epsilon sub h, elastic and plastic. We can examine these components in what's called a step cycle test, which is a very annoying test, but it does get the point across. And so what you can think about in terms of the deformation of a given polymer is that it looks like this. All right, that would be the normal behavior. And what they do is they take this process of straining, and instead of just continuously going up, they'll go up, and then they'll turn off the machine, or they'll take the stress down to 0, and it drops back down. All right, and what that represents is we have the sigma plastic, and then we also have the sigma elastic. All right, and so you can just keep doing that up and down, up and down, up and down, up and down, and keep ferreting out the two contributions. And so part of this is doing what it's supposed to do, which is snap back. Let me think of that as being elastic, and the other part of it is not coming back, and that's the plastic. That's the irrecoverable strain in the system. All right, so we look at plastics as having both of those components to them in terms of what determines that overall strain in the system. Okay, and so entropy is doing one, and then just deformation that's irreversible is doing the other. And so we have both of these contributions that make up the yield of these plastics. Hopefully that makes some sense. And so this process allows us to separate out the two components. And so what we've got here is this upper one is sigma plastic, and this lower one is epsilon elastic, not sigma. And so what you see is initially there's a pretty small contribution of the plastic, and then that starts to grow substantially as we get to larger values of overall strain. And then conversely, the elastic starts out relatively high, and then finally it reaches a kind of a plateau, and then actually starts to drop a little bit as we go to larger and larger values of strain. And so we separated this out using this step test to give us a decomposition of the strain, giving us features that are typical for these semicrystalline polymers. And that, when I say semicrystalline, you should be thinking clock diagram, right? Because that's what the clock diagram refers to as a semicrystalline polymer. And so the elastic strain reaches a maximum value on a plateau. This occurs at the strain where the strain hardening sets in, or about 0.6 on the overall strain level. Plastic strains develop from the very beginning. It's pretty small at the beginning, and not as in metals, only for strains above a certain point. So there's hyperplastic forming of metals, which is a very big deal. It has almost no elastic behavior because it's going so fast that it behaves like a plastic material. The plateau has only a limited extension, and the elastic strain then starts to decrease, as you saw in that plot. And so additional observations from these tests show that rubber-like retractive forces in these systems. What does that mean? What do we know about rubber or rubber bands? They go back courtesy of what?
Thermal, like if you heat them up, especially, but...
Well, with a real rubber band, we don't need to heat it up for it to snap back. Why does it snap back?
I know, the
Crosslinks, so it's an elastomer. All right, so yeah, it snaps back because crosslinks drive it back. All right, in this context, we talk about it as a rubber-like retractive force, even though we don't have crosslinks in the system. And again, the failure of the imagination on the polymer community. They call these crosslinks but they're not really. These non-crosslink systems are created not only by intersections with crystallites, which is important. So again, polymers have to go into the crystals and come out again, so those crystals can kind of restrain that, but also by entanglements, which is probably a lot more appropriate. So when you have one polymer chain overlapping with another polymer chain, we can think about that as sort of like a crosslink. All right, it's not the same thing. Again, I didn't name this, but it's how they think about it, that those entanglements can try to pull the polymers back to where they used to be. All right, because you can't get rid of the entanglement. Crystallization from the melt does not remove those entanglements, but just shifts them into the amorphous regions. And so again, the clock diagram is saying that we have crystals, and then these entanglements tend to get shifted out into that amorphous region, so they can help pull things backwards. And these are entanglement networks that are preserved to relatively high total deformations. Why? Because the polymer chains would have to break chemical bonds, first off, which is hard to do, or it has to be something where it pulls one string out from the other, which is only going to happen at low molecular weights. Okay, but it can happen at really high deformations. All right, and so this is an example of that, in which we take polyethylene with a high crystallinity, so clock diagram, stretched to different extensions lambda. Again, we're talking about this lambda, in this case it's on the vertical axis. And then what happens is they actually open the clamp and they allow it to shrink, and they look at that initial shrinkage. And so what you're doing is you're taking polyethylene, straining it, and then you open the clamp and you go through this thermal cycle. All right, and so we're going through this cycle of heating that's pretty quick in the scheme of things, and during that cycle of heating it all drops back down, pretty much in this first case back to where it was. That's full elastic recovery. Instead you go to a slightly higher value of strain, or lambda is higher, and it kind of goes back as well, and then this third one eventually goes backwards. Now keep in mind, this is a lot of thermal annealing, if you want to call it that. You're giving a lot of time and temperature to recover like this. But even under those pretty generous conditions, if you go to a high enough value of lambda, 3.2, so it's 300% its original length, we end up with something that is non-recoverable. All right, and so there's that plastic strain, even if you give it all kinds of energy to let entropy drive it back to its original dimensions. At some point, this is not able to restore those initial dimensions, because matter has just moved around too much for entropy to bring it back to the original shape.
So that's like when you get to what's called plastic deformation, or
you have permanent plastic deformation. Sometimes they call it permanent set. You see that term used elsewhere. But this is sort of an extreme case because you're really trying to get rid of it, working very hard to get rid of it. But even that's not enough. All right, so entropy mostly wins, as you see here, but at really high values of overall strain, even entropy can't pull it back to where it used to be. And entropy, entanglements, everything else that's working in favor of that is not enough. Any questions about that? So what's happening in this context, when the sample is heated, shrinkage continues. When lambda is less than 2.5 or 250%, returns to its original dimensions when we reach the melting point, representing the return of the entanglement network to its original isotropic, lower entropic energy state. When lambda is greater than 250%, recovery is not complete, indicating that some disentanglement has taken place. All right, so you've pulled polymer chains out from each other, probably because of some of the higher energies that are involved in these systems. And so that's going to give you a system that doesn't come all the way back to where it used to be. Any questions about that? We're going to finish up here in a second. So hopefully that all makes sense. Again, make sure you're familiar with the clock diagram. All right, and so this is the sort of talking about the next step. And so again, that clock diagram would go all the way over to where the blocks are breaking up, Okay, so now it's just not the amorphous phase that's involved in deformation, it's the crystalline phase. And so what you've got is this issue in which strain controls gives you strain internally that's non-homogeneous in that semi-crystalline sample. So again, the clock diagram, the blocks break up, all right, the chains pull them apart, they start to slide relative to each other, and we're seeing that here as well. Crystalline lamella can exhibit a granular substructure in which nanometer-sized crystal blocks are the basic element. We saw that in the prior lecture. And in this case, sliding motions of the blocks against each other provide sufficient degrees of freedom to accommodate any imposed strain. In other words, that you can really stretch out those crystalline components to being pretty skinny blocks overall. And so this is just showing you the net result. So first off, in your mind's eye, you should certainly remember that there are polymer chains coming in and out of these. They may be going to their neighbors. They may be going off into infinity. They can go from one block to the other and then go off into infinity. There's all sorts of polymer chains involved here. And in many cases, these are going straight up and down, which is why we see the deformation that we do. But the original shape of this, you should think of as being, and I'm going to strain my art skills here, should be something like that. So originally this used to be a couple of nice flat crystals. Yeah, that's not too bad. And then we applied those overall values of strain, and they started to separate where the polymer chains go in and out. And it turns into that, ultimately. Okay, does that make sense? And this is what's called inhomogeneous strain at that local level. All right, so obviously these guys are not all pulling in the same direction at the same time. All right, that's what's inhomogeneous about it. And we also, at these interfaces, we must be getting melting. All right, so polymer chains, in order for these blocks to slide past each other, polymer chains must no longer be crystalline somewhere at that interface. All right, so you've got a little localized melting that allows them to slide because we now have amorphous polymer chains between them. And a nice thing about this is we can see it. And so this is a TEM of another polymer you do not need to memorize, poly-L-butene. And I think I mentioned this before, is that electron microscopy and polymers don't get along really well, and TEM especially doesn't get along really well with polymers because it's a high beam energy. All right, and so it'll melt the polymer, generate gases, and the TEM technician will kick you off the machine and never let you use it again. All right, so don't do this. And what they're doing is they take this material before and after strain, and they use a carbon replica. They deposit carbon on it, peel the carbon replica off, and put that in the TEM. And that's okay, because carbon doesn't do anything when you heat it up inside the beam. And so what you're seeing is what I just gave you a little cartoon of, except that you can see these broken up blocks. They've all shifted. It's all over the place. If you start to look closely, you see how they're broken. And they used to be, a straight block, but then because of the polymer chains going in and out of it, they sheared relative to each other. So you see that everywhere. All these lines consist of the original crystallites, lamella in the system, that have been broken up and shifted around relative to each other based on those overall applied strains. Okay, so we can see this, we know what occurs, and it's all part of the clock diagram deformation of these materials. And then finally, if we take this further, rather than just talking about individual crystallites, we've already talked about spherulites. So what happens to spherulites? They are composed of these crystallites. And so that happens inside the spherulites, but you can see this in the context of a structure. So we have an example of the Maltese cross patterns here, right? So we know what those are. We know it's an artifact. It's not real. And when we start to strain this, we can take an initially isotropic sample and deform those spherulites. And if you keep going, further strain can destroy them and create what is called a fibrillar structure. And so that's what you see here, where you've taken a spherulite and you've smeared it out. All right, you strained all those pieces, and within those pieces, these crystallites are breaking up, but there's some vague resemblance to the initial microstructure. All right, so just to let you know, it can be observed when you start out with something that's very highly crystalline as well. Okay, we talk about these crystallites as being little rocks, but they're still plastics. All right, they're still organics, and so it's pretty easy to strain them. And in doing so, you strain these microstructures that consist of spherulites. And then last but not least, connecting this to the last lecture, you can see an X-ray diffraction for the same reasons. All right, the alteration of what was the original isotropic patterns, where everything was nice and symmetric, you start straining everything, and you start limiting the number of directions that those crystals can point in, just like before. And so the spheres or the circles break up into arcs and then ultimately into points as you keep straining and straining and straining these systems. Okay? Any questions about all that? When is the test?
Friday.
All right. Polystyrene, recycling number?
6.
Oh, that's much better. Okay. All right, good. Okay, I'll see you guys on Friday.